Okay, so 8.2b, we are going to do a little more with confidence intervals on P problems, and we're also going to learn a really nice shortcut on your calculator that I know you guys are going to enjoy. So let's jump in. Our textbook kind of takes these style of problems. Chapters 8, 9, 10, 11, the next 4 units really, kind of even chapter 12. So basically the rest of this class follows a pretty similar process, and our book calls it the 4-step process. So when you do problems with statistical inference, where you're making predictions or estimates about a population parameter, you're going to use this 4-step process. And at first, it's a lot to keep track of. And it's like, oh gosh, am I going to remember all of this? But you will get really, really comfortable with this stuff pretty quickly. And you will end up liking this sort of question by the time you get to the AP test, because it's like the same sort of format again and again. It makes a kind of abstract, crazy concept really doable. So you will like these problems and you will enjoy it when you see one of these on the AP test, because you're going to know exactly what to do on them when the time comes. So the 4 steps are written down right here, and we'll talk about that as we get into our example. But state, plan, do, and conclude are what the book calls our steps. Now, there's a really handy calculator command that you're going to be able to use when it comes to doing confidence interval and actually all sorts of problems. So let me show you where that button actually is. This is going to be your new favorite menu in this calculator as we get into second semester. You're going to go to the menu that says Stats. And then over here, we've used Edit, we've used Calc before. We've never used this third menu called Tests. There are a ton of different commands in this menu right here. We're going to learn I don't know, 10, 12 of these by the end of the class. For right now, though, our first option that we're going to learn is choice A, which is called a 1 prop Z interval. 1 proportion Z interval. So let me show you where that button is, or tell you what to write down here so you can find it later. You're going to go to Stats, and then the Tests menu, and it's going to be number A, which is a 1 proportion Z interval. We will learn a bunch more of these commands later, but for now, this is the one we're going to use. And we'll practice how to actually use it when we do our example in just a bit. But really helpful menu that does a lot of good stuff for us. And the AP test is actually surprisingly okay with you just using your calculator for that step of the process. So, our main example for the day is kind of a cool little science experiment here. I think this is neat. We have a little first grade girl, and she learned in school that 70% of the Earth's surface is supposed to be water. So she wants to know if that's actually true, and her dad do like a little science experiment where he has an inflatable globe. He's going to toss it to her and presumably spin it as he throws it in different ways. And she's going to put her finger on the globe in different spots and point to wherever it lands and see if it's water or land each time. So in order for this to actually work out, the globe that they're using has to actually be like proportional to the Earth. If the globe's proportions were off, that obviously wouldn't work. Also, it needs to be where they're actually spinning it and it's random when they do it and not just like handing it to her like this each time. But if those things are true, it seems reasonable that you could call this a random sample. So anyway, they want to make a confidence interval for the proportion of the Earth's surface covered in water. When you see this, there'll be a problem where it's like construct and interpret an interval. Even if the problem doesn't explicitly say to do so, this is going to be a situation where they just give you a bunch of space like this where you use the 4-step process. The first step of the 4-step process is the state step. In the state step, you're going to define your variable. So I'm going to write down, we want to estimate. So like, what are we even trying to do? Well, we want to estimate P equals, my variable for a proportion problem is always P, that's my parameter. P is going to be the true proportion of the Earth's surface covered in water and we want to do it with A, they say to use 95%. So we're going to do it with a 95% confidence interval. So this problem will be like your model for when you do your own 4 steps. Your first step is just say we want to estimate. You define your parameter. You say what level of confidence you're going to be working with. So that step states done. The next thing we're going to do is do our planning step. And in our planning step, we're going to address our 3 conditions that we learned about. So the first condition is random sample. And like I said, it depends if it's actually been spun and it's like random, but we're going to say it's reasonable to assume the 50 spins represents a simple random sample. Okay, so it's reasonable to assume those 50 spins are representative of an SRS. Our next condition is the 10% condition. Now, technically, the 10% condition comes into play when you are sampling from a population without replacement. It comes up in surveys all the time because when you pick somebody, you don't pick them again. That's when you need to check the 10% condition. In this situation, they're just spinning a ball and they're not like taking a spin that they can't use again or anything like that. So there's no sampling without replacement. So the 10% condition technically isn't necessary here. I'm going to emphasize that more in chapter 10 though. So if you were uncomfortable with that or if that didn't make sense, it's easy enough to say that 50 is less than 10% of possible spins on the globe. You could also say that spins are assumed to be independent. And then you don't have to address the 10% condition at all, because if the spins are independent, there's no need for approximate independence. Either way you want to do that is okay for the 10% condition. And the last condition is that n times p, n times 1 minus p. Remember what I said last video, don't write the symbols, just go straight to the plugin. N was 50 trials. And then we got 33 out of 50. I like leaving it as a fraction because the 50s cancel. You just get 33, totally greater than or equal to 10. And then I'm also going to do 50 times 1 minus 33 over 50, which would be 17, also greater than or equal to 10. That tells us that the distribution, technically the distribution of p hats, is approximately normal. If you just want to say approximately normal, that should be good enough. So that's my plan step. States, do the variable. Plan, check your conditions. Now it's time for the do step. And in order to set up your do step, one option you have is you do our sweet formula from last section that we just got done learning. You plug into this and you just show your work. That's all you would do right here is plug in stuff, do it like the last set of slides. That would be fine. To save time, I'm not going to do that this time. Instead, I'm going to show you the new calculator option. So I'm also going to clear this all out so I can have more space to write. So for the do step, if you're going to use your calculator, what you need to do is go back to that stat menu, go to tests, and choose choice A, 1 prop Z interval. The X and the N that it gives you, N you should know is 50, number of trials. X is the number of successes. So how many times you got what you were looking for? We got water 33 out of 50 times. And they say to do a 95% confidence interval. I should calculate, and it's going to spit out everything I need. So this feels almost like cheating, like where you're not showing enough work. Like, because you would think they want it, math teachers always tell you, show all your work, do all your steps, do it by hand, don't trust the calculator. But AP Stats is a lot more concerned with how you analyze things and how you use that information, that they're actually cool in a free response question with you just grabbing the answer off the calculator, okay? If it's a multiple choice question, you still have to know your formula because they can make it so it just shows you the pieces. But for a big old free response question like this, you can feel free to use the calculator. You need to report 2 things, the name of the command or the name of the test, whatever, and the interval that we got. So it's 0.52, let me write this down so I have it, 0.5287 to 0.7913. All right, so what I would do for my do step, I would write down the name of the test, 1 proportion, z interval, and I would put my answer. My answer went from 0.5287 to 0.7913. They are actually okay on the AP test with just showing that. That gets you full credits. It's not a good idea to also show your work if you feel like, oh, I got to show my work, and you do that extra. Because anytime you give 2 answers, if they don't match on the AP test, they always grade the worst of your 2 answers to punish you for giving 2 they're called parallel solutions. So I do not advise you to also write down the plugin unless you're sure it equals the same thing. If you go calculators, go calculator for a problem like this. You could get the same answer by using what we talked about last video, but this is just easier, quicker. So the last thing you do is your conclusion, and that's where you give me the script that we've been practicing. You interpret this interval. So you would say that we are 95% confident that the interval from 0.5287 to 0.7913 captures the true proportion of Earth covered in water. So by now, we've practiced that script even before you knew it was going to be part of this 4-step process. That should be just cool. Just write down your little scripts and we're good to go. You have context in there. Everything is lovely. So what did they just figure out? Well, based on their experiments, without actually sitting there and like measuring the percent of the Earth covered in water, based on their 50 trials, they can be reasonably certain the answer is somewhere between a 52% and a 79%. Is that a big range? Yeah, they did 50 trials. You do more data, you add in extra trials, and that margin of error will begin to shrink. Now, this is important if you are a calculator kid, which most of you are going to want to use this sometime or another. I am not going to help you with this if it happens on the test. I will act like I don't know what's going on. But when you use the calculator option, you need to be careful, because if you take 33 out of 50, that's a 66%. So their p-hat, their sample proportion, was 66% in this problem. Sometimes the problem just might say, oh, it was 66%. They wouldn't give you the 33 and the 50. So what kids will do is they'll put the 50 trials, but then they'll be like, oh, it's 66%. So I put 66% right there. If you do that, it will say error. This calculator command needs to have a whole number of successes. So you guys should be able to figure out how to turn 66% back into a fraction. Like, you should be able to work that out. You've made it to AP Stats. You should be cool there. Even if you round it and it was like, oh, I think it's 33.1 or 33.7 or something like that, any sort of decimal right here, and the calculator will reject it. So round it to the nearest whole number, up or down, whatever. But if you sit there and you're like, oh, my calculator's not working, I can't help you with that on the test. You need to make sure you're aware X needs to be a whole number, rounded if it's not. So yeah, that is how you do one of these problems here. And you'll get really, really good at them with practice. Last piece of this section. Sometimes you may want to have a certain margin of error. So you may be like, I'm comfortable being 5% for my margin of error on either side, or maybe I want 3% or 4% or 10%. But it's reasonable when you're collecting data, before you get your data, you may know about how wide you want that interval to be. And the 2 things that you can do to influence that margin of error are the confidence level, which you can only do so much with that. Like 95 is kind of the go-to. So like you don't want to change that too much. The other thing you can do to limit your margin of error is you can increase your sample size. So this right here, this guy is just your confidence interval formula after the plus or minus. This is just the after the plus or minus part of your formula. What you can do is take that guy and put it less than or equal to whatever margin of error you are comfortable with, and it'll solve it for you. So if I want a 4% margin of error, I can just do less than or equal to 0.04, and I can solve this formula algebraically and figure out how many people I need to talk to. So if I'm like, oh, I want 4% for my margin of error, okay, I can do some quick, easy math, and I can figure out what number of people to talk to so my margin of error is where I want it to be. Now, you're not going to have your data when you actually doing this math, because this is like before you get your data, where you would need to figure out how many people to talk to. So you're actually not going to know p hat, because p hat comes after you get your data. But if you got your data, then you already have a sample size, and it's just things are out of order. So if you're trying to figure out your sample size, what you do is you either A, guess what you think p hat's going to be. It feels like about 30% of people are going to be this, and you can use that and just guess with your p hat if you have an idea, or if you have prior data that tells you it's going to be around such and such. You also, if you just, I just don't know what my proportion is going to be, the worst case scenario in this formula, the biggest this thing can be, is if p hat is a 0.5. So if you're like, gosh, I just don't know, or I'm not confident enough to say what p hat might be, use a 0.5, and that is a worst case scenario. Then even if you like it ends up being not 0.5, you're actually going to be even better off. So your margin of error will be even smaller than what you wanted it to be. Okay? So you're going to take everything after that plus or minus sign, less than or equal to whatever margin of error you're comfortable with, be it 0.04, 0.03, 0.10, do a little math, and you can calculate your sample size. I'll show you how that works in an example. So you want to figure out the true proportion of students at a large school who have a tattoo, and you want to do 98% confidence, and you're comfortable with a margin of error of no more than 10%. You don't want to be more than 10% each way when you make that interval. So what you do is you take everything after the plus or minus sign, critical value times standard error. So all of this stuff right here. And it's going to be less than or equal to your comfort level, which in this case is 10%. Now there's that 98% right here. That's going to get us our critical value. So I would need to do a quick thing. That was a real bad normal curve. I would do a quick inverse normal, just like I taught you last lesson to get your critical value. My area to the left would be a 0.01. And if you do that, it's like 2.326. So what I'm going to have is 2.326 times. This problem doesn't give me any sort of indication what we think the answer might be. And you could always guess, I think it's 20% of kids who have a tattoo. But if you guess wrong, your margin of error can actually end up not working like you want it to. So if you truly don't know, just use 0.5 for P, which is like a worst case scenario. So if you use 0.5, that'll be the biggest this quantity can possibly be. We don't know n. That's the whole point of the problem, is finding n. And we have less than or equal to a 0.10. This is actually like an algebra 2, just get a variable by itself situation. So do math, basically. I would divide by this number first. And you guys are all smart kids watching this, so you can figure out what you would do here. So I do my division. So divide by 2.326. After that, I would cancel out my square root by doing a squared to both sides. So I'm going to square that guy. When I do that, I end up getting just the 0.5. 1 minus 0.5 is also 0.5. And it's going to say on this side, I have 0.001848. Lots of decimal spots is better. If I'm going to solve this for n, I would have to get it out of the denominator next. And then I have this guy, which is I think it's 0.25. Yep. So I would want to divide by the 0.001848. I'm boring you right now with math you should probably already understand. And when I do that, I end up getting a 135.25, and I have n over here. So in order to get the margin of error that I wanted, which admittedly is pretty big for this problem, normally you would probably want to go a little lower. I would need to talk to 135.25 people or more. always bump it up to the next whole number. Never report a decimal because these are people you're talking about. Don't do that. So you always, doesn't matter round up, round down. That's not what we're doing. We always bump it up to the next whole number because you have to be greater than this thing right here. So you need at least 136 people. So this is kind of handy. It's like a little consequence of our formula right here. If you know the margin of error you want, you can do a little quick math and you can figure out how many people you need to talk to.